In part 2 of this screencast, we're going to look at another situation where what if you had have added the same exact amount of the strong acid or strong base, but instead of adding it to a buffer solution, what if you put it in pure water? Now remember, the pH of pure water is always 7.00 at 25 degrees Celsius. So for the first situation, when we added the strong acid, if we add it to pure water, since there's no buffering components in pure water, to find the pH of that solution, the new solution, you would take the negative log of 0.10, because that would be the hydrogen ion concentration, and that would give you 1.00. So the change in pH to pure water upon the addition of 0.1 molar HCl would have been calculated by taking 7 minus 1, which gives you 6.00 for the overall change in pH to this unbuffered system. Now, remember from the last example, when we added the same exact amount of the same exact acid to the buffer system in the last example, the change in pH was only 0.32. And that's the whole point of a buffering system. It resists a change in pH. If you need the pH buffered within a certain range, you want a buffer system with the common ion present. Now, the second example that we looked at was when we added the strong base. This was from the bonus example. So if you were to have added the 0.20 molar sodium hydroxide to just pure water, we would calculate the pOH first, and we would have gotten 0.70, and then to get the pH, 14 minus 0.70 would give us the pH of 13.30. So in this instance, the change in pH would be 13.30 minus 7, because that's what it was originally, which gives us a delta pH. Upon the addition of this strong base, the change was 6.30 pH points. Now compare that to the buffer problem where we added the same exact concentration of the sodium hydroxide but to a buffer system. The change in pH was only 0.56. So notice again, the purpose of a buffer system is to keep the pH within a certain desired range. So this leads us to our final part for as far as buffer systems go, and that's referring to something we call buffer capacity. Buffer capacity represents the amount of hydrogen ion or hydroxide ions that the buffer solution can absorb without a large change in pH. So the amount of hydrogen or hydroxide that the buffering solution or buffer system could absorb without a large change in pH. The greater the buffering components, so what I mean by that is the greater the concentration of the buffering components, the greater its buffer capacity. They're directly related. Now, one very important thing to keep in mind is the optimal buffering is going to occur when the concentration of the weak acid is equal to the concentration of its conjugate from the salt. So that's the conjugate base in this case. If you were to have a weak base, so I'll use ammonia as my example of the weak base, if its concentration was equal to the concentration of the ammonium ion, conjugate acid. So when these concentrations are equal, if you look at your Henderson-Hasselbalch equation, that's when optimal buffering occurs. And here's why. If you consider the Henderson-Hasselbalch equation, when these two are equal, you end up getting 1. So the log of 1, plug it in your calculator, log of 1 is always 0. So that means pH equals the pKa. Anytime the pH equals the pKa, that is your best buffering system. So if you're trying to keep the pH within a specific range, what you want to do is find a weak acid or a weak base that has a pKa value closest to the desired pH. And then find its common salt and mix up a concentration of identical values. So if your acid's concentration is 1 molar, the common ion, the salt, should be 1 molar. If the acid concentration is 5 molar, the common ions should be 5 molar. In our next video, we're going to take a look at KSP, or solubility equilibria.